Okay, so next exercise 8. So here we are given a field F and we are considering this polynomial ring in two indeterminates x1 and x2. We have to prove that it's not a principal ideal ring. So we will show that a particular ideal is not a principal ideal. Let A be this subset of fx1, x2. Now we aim to show that this A is actually an ideal of this ring. Clearly A is non-empty, so we are not going to mention that. Let f1 x1 plus g1 x2 and f2 x1 plus g2 x2 be two elements in A. Where these are polynomials in the general ring. And then plus g1 x2 minus f2 x1 plus g2 x2 using all the axioms that are available in this ring. This difference can be written like this: f1 minus f2 times x1 plus g1 minus g2 times x2, where we have used distributive law and other things. And you can see that this again belongs to A, because f1 minus f2 is again in this ring, and so is g1 minus g2. Thus A is a subgroup of fx1, x2 under addition. Also, for any, say, what can we take? Let us take A. We have A times f1 x1 plus g1 x2 is equal to A f1 x1 plus A g1 x2. This again belongs to A, because A f1 and A g1 are in this ring. So A is an ideal of the polynomial ring. We now aim to show that this A is not a principal ideal. It cannot be generated by a single element in this ring. Contrary to that, we will suppose that that is actually the case. Suppose A is the principal ideal generated by H for some element H belonging to the ring. Okay. Then H is equal to fx1 plus gx2 because since H itself will belong to this, so our supposition implies H is in A. So H will be of this form. It will be a combination of x1 and x2 with coefficients coming from the ring for some f and g belonging to this. Okay. Now let's look at the elements of A. Elements of A are linear combinations of x1 and x2. In particular, if we take f to be the constant polynomial 1, where 1 is the unit element in f, and g to be the 0 polynomial, then we get x1. That means x1 belongs to A. Now, since x1 belongs to A, we have x1 equal to say kh. x1 belongs to A means x1 will be a multiple of h, since this is our supposition. So every element in A is a multiple of h for some k belonging to this. Since fx1 comma x2, see, by definition, by the original definition of this ring, this is actually the polynomial ring the polynomial ring in the indeterminate x2, where the coefficients are polynomials in x1 over f. So because this is true, so that's why, so what is the argument here? x1 itself is also a polynomial in x2, namely actually a constant polynomial. If you think about it, x1 is a polynomial in x2 that is constant because there is no x2. The element x1 that is coming from this ring fx1 can be treated as a ring element, so constant. And because of that, the left hand side is a constant polynomial in x2, whereas k and h, they are general polynomials in x2 over fx1. And to this equation, if we now apply that degree formula that we proved in exercise 3, then the degree of this should be equal to the sum of the degrees of k and h. since this is equal to this, exercise 3 implies zero equal to degree of x1. You should clearly understand what this equation means. We are calculating degree of a polynomial in x2, that is, we are calculating the degree of x1 as an element of this ring. Okay, so that's why its degree is 0, because in x2 it's a constant polynomial, and that is equal to degree of k h, which is equal to degree of k plus degree of h. Hence, the same interpretation also is applicable for degree of k and degree of h. This is the degree of k as a polynomial in x2 with coefficients which are polynomials in x1 over f, or simply which are with coefficients that are from fx1. Okay, so we have this. Hence, degree of h and degree of k are both equal to 0. Degree of h being 0 means what? It means that as a polynomial in x2, h is constant. In other words, h belongs to fx1. Degree of h equal to 0 implies h belongs to fx1, and actually k also belongs to fx1, but anyway, so we have got this. Similarly, using the fact that fx1 comma x2 is actually isomorphic to fx2 comma x1. Here in fact you can use you can refer to that exercise. You know what I am talking about. We came across this, the exercise which says that if we are in a multivariate polynomial ring, then we can rearrange the indeterminates in any order we want according to whatever permutation of this vector we may choose. That one. Okay, we can refer to that exercise, but I don't remember the number of the exercise exactly. So I am just simply writing. Similarly, using the fact that these two rings are isomorphic, we have h belonging to fx2. For this conclusion, we have to start from the fact that x2 belongs to A, and then x2 will be a multiple of h for some k prime, say, and then you argue similarly where in place of this you will have fx2 x1. Using that and a similar argument, we will ultimately end up with this h belonging to fx2. Okay. So that means h is a polynomial in x1 as well as a polynomial in x2. But then by the definition of equality in our original ring, we must have h belonging to f. If h is a polynomial in x2 where actually there is x2, then it cannot be a polynomial in x1 over f. Yes, it can be then also be a polynomial in x1 over fx2, but that is a different thing. This means h is a polynomial expression in x1 with coefficients coming from the field, and this means that h is a polynomial expression in x2 with coefficients coming from the field. These two things can happen simultaneously only when h is in f, that is h is a field element, and this follows from the definition of equality of two elements in this ring. Also, since a is not equal to 0, a is not equal to 0 because, for example, this non-zero element x1 is in a, x2 is also in a, we must have h not equal to 0. It's because a is being generated by h. If h is 0, then a must be equal to the 0 ideal, which is not true. Okay, so now we have the information that h is actually a non-zero field element. Now we are going to use this equation. Okay, what can we conclude from this equation? The actual conclusion is this: since the constant, although we did not define anything called constant term, but you will understand what I mean by constant term. Since the constant term of fx1 plus gx2 is 0, the constant term is the single field element that we have in this polynomial, which in this case is 0. You see, whatever f and g may be, they are being multiplied by, f is being multiplied by x1, g is being multiplied by x2. So ultimately, after multiplying and after forming the sum, we will not have any field element outside other than 0. So that field element we are calling the constant term. It's, if you have a polynomial like this in x1 and x2, say x1 to the power 4 minus 2x1 to the power 5x2 minus 3, say, and suppose the field is the field of real numbers, then this minus 3 is what we are calling the constant term of the polynomial, which in this case is 0, which you can clearly see. Since the constant term of this is 0, the equation h equal to fx1 plus gx2 what can we write? It produces a contradiction. It actually contradicts the fact that since that constant term is 0 and since the polynomial according to this equation itself is constant h, which is a field element, h must be equal to 0, which is not true. Okay, so we can write like this. This equation implies h is equal to 0 since h belongs to f, which is a contradiction. Thus, our initial supposition is wrong. That is, A is not a principal ideal. That means A cannot be generated by a single such polynomial h. Hence, this is not a principal ideal ring. Okay, so we have completed the solution. Now, what is the consequence of this exercise? Note that while discussing about these multivariate polynomial rings, we mentioned the fact that this type of rings are not necessarily Euclidean rings. Now, because of this exercise, we can say that for sure this particular ring is not a Euclidean ring. Why? Because in the theory of Euclidean rings, we have seen that every Euclidean ring is a principal ideal ring. This is not. So that means this cannot be a Euclidean ring. But in the theory of Euclidean rings, we also proved that every Euclidean ring is a unique factorization domain. From our theory of general polynomial rings like this, we have already proved that this is a unique factorization domain. So this particular ring is an example of a unique factorization domain that is not a Euclidean ring. Okay. So that conclusion we can draw from this exercise. Let's see the next one. Nine. Prove completely lemma 3.11.2 and its corollary. Okay. Now, before we write the solution, let us recall the statement of this lemma. The statement is this: if R is a unique factorization domain and A and B belong to R, not both 0. That means both A and B are not equal to 0. At least one of them is non-zero. Then A and B have a greatest common divisor. Which we denote again with the usual notation in R. So this is one half of lemma 3, 11, 2. And there is another half which says, moreover, if A and, okay, let me just take some ink. If A and B are relatively prime, that is, if their GCD is a unit, which is equivalent to assuming that their GCD is actually 1, and A divides BC. Yes. Then A must divide C. Okay, so let us now prove this lemma. So at least one of A or B is non-zero. When one of them is 0, then the situation is particularly simple. So we assume without, okay, we cannot write without loss of generality exactly, but we assume both A and B to be non-zero, and the reason is this: if A is 0 and B is non-zero, for example, then this is equal to B. One can see that the definition of greatest common divisor that we have given for two elements in a unique factorization domain, this is true in this case. So that's why we can assume both A and B to be non-zero. Okay, now what happens if at least one of them is a unit, is an element that has a multiplicative inverse in the ring? If at least one of A or B is a unit, then the GCD can be taken to be equal to 1. Why is that so? You go back to the definition of GCD and you try to figure this out yourself. Okay, when at least say A is unit, whether B is or is not unit we don't know. In that case, you try to argue that the unit element 1 in the ring is a greatest common divisor of A and B. Okay, so I am just leaving it like this. So we have assumed that both A and B are non-zero, and in this case also the result is trivially true. So now we are further going to assume that A and B, apart from being non-zero, are also non-units. So we further assume that A and B are non-units. So that means we have two non-zero non-unit elements A and B in R, which is a unique factorization domain. So that means each one of these elements A and B will have prime factorizations. So next we are going to consider that. Let A be equal to this and Q1 to the power beta 1 etc. Qn to the power beta n, where P1, P2 etc. Pm, Q1, Q2 etc. Qn belonging to R are prime elements and are positive integers. Now since we are considering powers of prime elements, so it makes sense to assume that these pi's are actually distinct. If they are not, then say if p1 is actually equal to p2, then in place of this product, this part of the product, we can write p1 to the power alpha 1 plus alpha 2. So we can conveniently assume that they are distinct. However, distinctness does not mean literal distinctness, but that these are not associates. Okay, so that we mention here. PM are distinct and so are the QJs. Note that here distinct means not associates. Okay. Let us now define a set. We are going to use that set. Let, it's not something that we absolutely need, but it will make the presentation of the solution much better. Let A be the set of those C belonging to this list of prime elements such that C is an associate of some element in the other list of primes. So this is my set A. Now we are going to look at two cases. The first is when A is empty and the second one A is non-empty. So what happens when A is empty? We already have the unit element 1 dividing both A and B. Okay. And now is it possible for something else to define both A and B? That is not a unit. If there is an element, say A, we cannot take A. So say there is an element C that is not a unit, also not 0 obviously, because we are talking about divisibility by C, that divides both A and B. If it happens, then according to the fact that C is an element in a unique factorization domain and is a non-zero non-unit element, C will itself have its own factorization. In that factorization, there will be a prime element. That prime element will divide C, and hence that prime element will divide both A and B. So if it happens that a non-zero non-unit element divides both A and B, then there must be some prime element in the ring that also divides A and B. Now is this possible? That's what we have to see now. And for that we are going to suppose the existence of such a prime. Suppose there exists a prime element pi belonging to R, which of course is not the number pi, you have to understand that, such that pi divides A and pi divides B. Okay. Now pi divides A means what? The relation pi divides A implies equal to A equal to pi, say, gamma for some gamma belonging to R. Now we have the fact that any factorization of an element in R is unique up to associates. This is the original factorization of A, but from here we will get another factorization. In that factorization, if it happens that gamma is 0, okay, then the right hand side will be 0, which will be a contradiction. Why will that be a contradiction? Because you see, these are all non-zero elements, so their product in a unique factorization domain cannot be equal to 0. So gamma cannot be 0. If gamma is non-zero, then gamma is either a unit or a non-unit. If gamma is a unit, fine, then we have two factorizations of A. One of them is this and the other is pi times gamma. Both are prime factorizations, keep that in mind. Now from the uniqueness of prime factorization of A up to associates, it will then follow that pi must be an associate of at least one of these primes. And if it happens that gamma is not a unit, that is gamma is a non-zero non-unit, then gamma itself will have a prime factorization. That along with pi will give us another prime factorization of A. From there also, using uniqueness of prime factorization up to associates, again pi has to be an associate of some pi. Okay. Should we write all these things, or I think we can, since you have I hope understood what we are going to now conclude, so instead of writing those things, we are directly going to write this, implies this. So from the uniqueness of the prime factorization of A, it follows that pi is an associate of some pi, where I of course varies from 1 to n. We are not writing that. Similarly, this will tell us pi dividing B implies pi is an associate of some, you look at the prime factorization of b of some q j. But being associates is an equivalence relation. We have already seen this before. So, since pi is an associate of pi as well as qj, so pi will be an associate of qj. But then pi is an associate of qj, and this contradicts the assumption that A is empty. A being empty means there is no pi that is an associate of qj according to our definition of A. Which contradicts this. So our supposition is wrong. That is, no prime element of R divides both A and B, that is, there is no such pi, and consequently no non-unit non-zero element of R divides both A and B. As a result, that means the only elements of R that divide both A and B are units. That's why we wrote here, we already have this. Besides that, there is no other common divisor. Thus, in this case, A and B have any unit as a greatest common divisor. Next, so this is the case when A is empty. Next, assume A is non-empty. In fact, let A consist of these elements pi1, pi2, etc. up to say pik. Okay, and in this case we are going to define an element. Define D to be pi1 to the power minimum of alpha I1 and beta I1. It's a product Pik It makes sense because these are originally positive integers, and hence their minimum exists, which is also going to be some positive integer. So the powers are well defined, so their product is a well defined element in R. Okay, so D is an element in R. Clearly, D divides both A and B. This follows directly from the definition of D itself. Since we are choosing the smaller among the two possible exponents, so D is going to divide both A and B. Also keep in mind that we are actually choosing the primes from this thing, which is those P's that are associates of Q's. Okay, now to show that D is a greatest common divisor of A and B, we just need to show one thing. If we have some other some other common divisor, say G, then G also divides D. So let now we should not write for some, let G be an element in R such that G divides both A and B. Okay. Let rho be a prime element in R such that rho divides G. Okay, such a rho will exist only when G is a non-unit in R. Of course, when we are going to take an arbitrary G in R, we will take units as well as non-units. So we are in general considering the case where, say, there is G is a non-unit, so that it has some prime factorization and rho is any prime factor of G. Now we are going to see what rho can possibly be. Then, since rho divides G and G divides both A and B, so rho will also divide both A and B. Thus, like above, like how we concluded the thing with pi, rho is an associate of, say, Pu and Qv for some indices U and V, whose variation you know. U varies from 1 to m, V varies from 1 to n. Then, okay, then Pu is an associate of Qv and hence Pu belongs to A. Okay, by the definition of A, Pu has to belong to A, and rho is an associate of Pu. Okay. that is rho is an associate of some element of A. So that's how rho will be, which tells us what about G. If G is a unit, fine. If G is not a unit, then it has a prime factorization. In that prime factorization, the primes will be associates of these primes. So conveniently, we can in fact take the primes appearing in the factorization of G to be in these primes themselves. The associate part, that can be taken care of by taking the units together and forgetting about that. Okay. So hence we can ultimately conclude like this: G is of this form. Yes, pi1 to the power gamma 1, say pi2 to the power gamma 2, etc., pik to the power gamma k, where gamma 1, gamma 2, gamma k, these are non-negative integers. In fact, to be absolutely specific about everything, we should also write a unit here that takes care of that the prime factors of G being associates of this thing. Let's just do that. Say delta. These are non-negative integers, and delta is a unit in R. Note that here we have taken care of all the cases. If G is a unit, to account for that possibility, we have allowed all the gammas to be 0. When they are all 0, then G is equal to delta, which is a unit. Otherwise, this is a prime factorization of G, which is a non-unit. Okay, so G now happens to be in this form. Now to prove that G divides D, we have to prove that each gamma j is less than or equal to minimum of alpha ij and beta ij, because then only division will be possible. Suppose that is not the case. Suppose note carefully that at every step we have only used the fact that the ring is a unique factorization domain. We have not used anything other than that. Suppose gamma j is strictly greater than the minimum of alpha ij and beta ij for some j lying between 1 and k. Okay, then we are going to use what? Okay, so if gamma j is greater than this minimum, that means gamma j has to then be greater than either this or both. or gamma j is greater than beta ij. We assume without loss of generality that gamma j is greater than alpha ij. Now we are again going to look at the prime factorization of A. And it looks like this: Pij to the power gamma j times, say, S. This is equal to A, and A is of course equal to has its own factorization, P1 to the power alpha 1. At some stage we will have Pij. Oh no, wait, this is not A, I think. Is it A or is it D? Okay, let's do the calculation with A. If things go wrong, we will look for an alternative. Alpha j Pm to the power alpha m. How? Okay, it seems that we have used the fact that Pij to the power gamma j divides A, because that's why we are able to write A as a multiple of this power of Pij. That is true because you see, originally we considered G to be an element that divides both A and B. Now since G divides A, and in G there is Pij to the power gamma j somewhere in this factorization of G. So Pij to the power gamma j must divide A also, since G divides A. So that's how we are getting this for some element S belonging to R. Now since gamma j is greater than alpha ij and Pij is not an associate of any of the other prime factors of A, uniqueness of factorization of A is contradicted. It's because you see, there is a we should have written alpha ij here. There is more Pij on this side than on this side. So if we write everything down without using exponents as a product, okay, written totally in that form where we don't use this exponent, so we will write p1 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 alpha 1 times, like that. If we write, then each such pi according to uniqueness of factorization should be an associate of some pj. And also uniqueness of factorization in fact says that these exponents should be equal. For primes that are associates, the exponents should be equal. that thing is contradicted here. So that's why this supposition is wrong. Hence, our last supposition is wrong. That is, gamma j must be less than or equal to minimum of alpha ij and beta ij for all j lying between 1 and k. So now we can finally say that G divides both A and B. So G divides both A and B. This implies, now what am I saying? G divides D, that is my conclusion. This implies D is a greatest common divisor of A and B. So in all the cases we have shown that A and B have a GCD in R. So this completes the proof. No, this, okay, I keep forgetting the things. This only completes the proof of the first part. We now come to the proof of the second part. Next, assume that A and B are two elements in R which are relatively prime and A divides BC. We know from above that this can be won in exactly two ways. First, if at least one of A or B is a unit. Okay, if at least one of A or B is a unit, then of course the GCD will be that unit, or in other words, the GCD will be 1. And the other case is that none of them is a unit, but they have prime factorizations where no primes in one factorization, no prime in one factorization is an associate of any prime in the other factorization. So let's first tackle this case. Okay, so now if we have to actually look at both the cases, not this one and the other one, but here itself we have two cases. Now if A is a unit, and what happens if B is a unit? If A is a unit, then of course A divides C, because any unit divides all the elements of a ring. If B is a unit, then A dividing BC implies, it automatically implies that A divides C. Why is that exactly true? Let us see. Let us see means I will just show it, I won't make it a part of the solution. See, A divides BC means what? BC equal to A times D, where D is some ring element. Now if B is a unit, then we can multiply on both sides by B inverse, giving us this. So that means C is a multiple of A, where the other element again is from the ring. So this implies A divides C. So that's how we get A divides C. Secondly, none of A or B is a unit, and the primes, or rather we should write like this, and none of the primes in A, in the factorization of A, is an associate of any of the primes in the factorization of B. Okay, then using A dividing BC, one can prove that A divides C. You may think that this is cheating, that we are just simply saying that this can be done, but I am going to give you the strategy for proof. BC equal to TA for some T belonging to R, and now use uniqueness of factorization. In this equation, you use uniqueness of factorization, taking into account the fact that in the factorization of A, no prime is an associate of any prime in the factorization of B. From that, you will see that you must then conclude that every prime in the factorization of A is an associate of some prime in the factorization of C. From that you will be able to show that A divides C. It's somewhat like showing that G divides D. Okay, so this I leave to you. So now finally this completes the proof of the lemma, but the solution is not yet over. We still have to prove the corollary. So let's state the corollary first. The corollary is simply this: if A belonging to R, where R of course is a unique factorization domain, is an irreducible element and A divides BC, then A divides B or A divides C. Now we are going to prove this, and that will end the solution. I mean, it will complete the solution. Okay, so if A divides B, then there is nothing to prove. Then we are done. So assume A does not divide B. If B is a unit, then also we are done. That means in that case we have A divides C. You already know how to show this. Write BC as a multiple of A and use the fact that B is a unit to write C as a multiple of A. So that will show that A divides C. So now assume that B is a non-unit. Okay. Since A irreducible means prime. Actually, irreducible, strictly speaking, does not mean prime. Primality of an element in a ring has a different definition, although the situations where we are considering primality matches with irreducibility in Herstein. Elsewhere, we will see a different definition of prime element. A prime element, if I am remembering it correctly, is an element in a ring that has this property. If it divides a product of two elements, then it divides at least one of them. If this happens, then we say that P is a prime element. We will discuss more about this relationship between irreducibility and primality later on. Okay, so since A is prime, and A does not divide B, no prime factor of B is associated to A, or we can write like this: A is not an associate of any prime factor of B. Hence, by the proof of that lemma, what is the number 311 to above, we have, so here again the argument is similar to what we previously had. So we have A divides C, and this finally completes the solution because it completes the proof of the corollary also. So this has been a long one. I'm ending the video here itself because I'm feeling a little tired today. So we will continue in the next video with more problems and more solutions from this set of exercises. So this is me, Lucifer, from a mathematical room. Until then, have a nice night.